Good evening, everyone. This is Rucha, and I handle membership engagement and industry initiatives at NASSCOM Pune. I, along with my team, welcome you all for today's session on Masterclass on simplifying the role of explainability in the MLOps cycle. In order to create more responsible and reliable machine learning models that generate accurate predictive outcomes, it is imperative to include explanations at various stages of MLOps pipeline with transparency, confidence, causality, and fairness in the pipeline. We can't fix the bugs in ML models like normal code. We can only iterate with better data, accurate hyperparameters, smart algorithms, and flexible system configurations to train the model. The MLOps pipeline helps to automate the workflow and consists of different components that are connected in a sequential manner. This masterclass aims to help you understand the role of explainability in the MLOps cycle and how it can enhance the prediction accuracy. Before we get started with the webinar, I'd like to go over a few important points that may help you to know how to participate in today's event. As an attendee, you will be on mute throughout the course of the event. If you have any questions, you can type them out in the Q&A tab at the bottom of the control panel. We'll try to cover as many questions as we can, and we request you to be as descriptive as possible while you list down your queries. Now, please join me in welcoming Dattaraj Rao. Dattaraj Rao is the Chief Data Scientist at Persistent, leading the AI Research Lab. He's responsible for driving thought leadership in AI/ML across the organization. He leads a team that explores state-of-the-art algorithms in natural language understanding, knowledge graphs, privacy-aware AI, MLOps, responsible AI, and demonstrates applicability in healthcare, banking, and industrial domains. Earlier, Dattaraj worked at General Electric for 19 years, building industrial IoT solutions for predictive maintenance, digital twins, and machine vision. Dattaraj is the author of the book Keras to Kubernetes, the journey of a machine learning model to production. Over to you, Dattaraj.
Thank you, Richa, for the very warm introduction. Hi, everyone. Great to be on this webinar. Thanks to NASSCOM, Rucha, Kritika, Sagar, and Kalpesh for inviting me for this session, and also Madhushri from Persistent for coordinating the whole effort. This will be a 1-hour session, like Rucha mentioned, and I'll try to keep it more interactive with some demos so that I can keep your interest. We'll talk about how operationalizing artificial intelligence. I mean, I'm sure I'm preaching to a choir. AI is everywhere. Most of the new projects that are going on leverage artificial intelligence in some form or other. And now there is a big push for standardizing on AI and ML. So there are, you'll see words like MLOps, which is DevOps applied to machine learning. And we'll talk a lot about it in this presentation. So one of the things that keeps coming up is how do you trust this ML model? So my talk will be more focusing on explainable AI. How do you incorporate explanations and interpretability into your AI models? And I would like to take a step back and talk about now explainability is one part of it, but a majority of it will be focused more on building AI in a responsible manner. So many companies, including Persistent, now when we put machine learning models to production, we have some stringent rules around responsible AI. We have to look at the transparency, security, privacy of the data. So all these things are covered under responsible AI. So I'll talk a little bit about that. And I won't keep this theoretical. I'll try to show you a couple of demos on how actually this can be done in practice, and so with some real world examples. So hopefully, so keep your questions coming. I mean, through chat at the end of the session, after the 1 hour, I can take in questions and we can go in detail of any specific topic. So let's get started. Rucha gave a very warm introduction about me. I'm the Chief Data Scientist at Persistent. About Persistent, I'm sure most of you are aware, we are like getting close to $1 billion company with offices all across the world. I think the latest we have more than 17,000 people, and we cater mainly to banking, financial services, and insurance domain, and life sciences and healthcare, and also growing into more of ISVs and high tech firms. My book, Keras to Kubernetes, that also covers the area around moving machine learning models to production. So I'll talk more about it into this session. So we'll start with as we are putting machine learning models and artificial intelligence into production. Why do we need responsible AI? So I'll give some real world examples of where AI actually had trouble and what was the reason for some of these. What are the foundations of responsible AI? And then majority of this talk will be focused on transparency, one of the major pillars of responsible AI. And that's what gets into the explainable AI piece of it. So we will, and the way we look at transparency, there are three stages. One is at the algorithmic level. You have to decide at the algorithm level itself, what is the choice you make on choosing the model building algorithm to look at explainability. Then we get into the business validation, where we look at more like what sort of explanations you are expecting and how just they are. And finally, when you put the model in production, you have to monitor the inferencing that is done by the machine learning model. So you also want to know that the results that the model is producing, what sort of explanations are tied to them, and is there any bias associated with it? So bias and fairness is something that is very much associated with responsible AI, and it also associates with explainability. So we will talk more about that, even things like how do you measure bias, and how can you even look at the data set to see if the data is biased. And then I'll try to spend a lot of time on demonstration, try to get a little bit technical. I know this is a technical crowd, so try to get a little bit into the technical details of it. And then we'll open up for questions. So let's get into it. So just some basic introduction, why we need responsible AI. I have two very high level reasons. The one is the ethical concerns about fairness bias. We all know that, data is the new oil and AI is the new electricity. But like they say, with great powers comes great responsibility. So you hear these sort of headlines in the news all the time. There was this Amazon's facial recognition system where they introduced a system to look at videos of faces and try to map to criminal mugshots. And they actually ended up mapping some members of Congress to the criminal mugshots, which obviously was not very welcome. You have algorithms deciding your credit score in the US or approving loans that you apply for banks. So you want these algorithms to be fair and not biased on unnecessary features like gender or a particular race. So that is something that AI models need to look at. So as we are seeing these different headlines coming up, so responsible AI is becoming more and more important, and companies are paying more attention the way they are putting models to production, how to keep them fair and explainable. The second part of it is around the hidden technical depth in ML systems. So as we are building machine learning systems, if you this is a very nice paper, I encourage you to look at it. If you look at the overall machine learning cycle, you typically spend a very less amount, the one that is shown in the black box, on actual ML algorithm development or code. In fact, in today's world, there are a lot of no code or low code machine learning tools. There are tools which can actually write most of the boilerplate code for feature engineering or for model development for you. So you hardly have to do any effort, or in fact, there is Stack Overflow or other sources where you could quickly copy the code. So you don't do a lot of work around ML development. But in real world machine learning models, you spend a lot of time putting the configuration of the system. You spend a lot of time data collection, data cleansing, verification, deploy. Once the model is created, deploying it, creating a serving infrastructure. Now, if you end up customizing each of this for every project, now there's a lot of technical depth because obviously you'll miss something. So today, MLOps focuses on having these frameworks which can have all these concerns already part of it. So there are frameworks like Seldon which can do a very good job of serving. So you can worry. So if you want to do an A/B testing of the models, or you want to do get into more like a multi-arm banding testing of your machine learning models to decide which model you want to put to production. based on user feedback. You can actually get into use Sheldon for a serving infrastructure to configure it. So a lot of work is going on around the infrastructure for machine learning, and that is the second reason we want to have a responsible AI system. Sorry, was that question? Okay. So and then let's take a real world case study. This is a famous example. In fact, it's pretty recent 2019 example of Apple Card. So Apple partnered with Goldman Sachs, and which is a major financial company, and they introduced a new card called Apple Card, and different people based on their different characteristics, spending history, demographics, gender, the income, the other factors, they applied for credit in the Apple Card, and surprisingly there was a bias in that algorithm which was judging the loan, the credit approval. Steve Wozniak, in fact, this is a famous tweet from Steve Wozniak, the co-founder of Apple. He said that he and his wife had the exact same parameters. The only difference was pretty much the gender, and then he could see that his wife got a 10 times less credit limit than himself. So this was a blatant discrimination that was happening while assigning credit, just purely based on gender. So this became major news. I think the Apple Card was withdrawn. So there was a lot of discussion. Why did this happen? Now, clearly, Apple didn't plan for it. I mean, they didn't say that, hey, if it is a female, we'll give them less credit. This was not something that companies do intentionally. This is something when the data was collected historically, there probably was the bias in the data which moved into the model. So this is a classic case of what we call fairness through unawareness, that they didn't really plan for it. In fact, the model probably didn't even include gender as a field while doing the credit calculation. But even then, even if you don't include so that is the principle of fairness to unawareness. Even if you don't include that particular feature, which is a protected feature like gender, race, caste, or something like that, religion, it will still be something that may affect. So you want to be able to consider that and make sure that your data set is not biased. And we will show in this webinar how do you measure this bias. So this was a famous case of the need for responsible AI. So these are the 5 pillars for responsible. When you are building machine learning models, putting them into productions, these are the 5 areas of focus that we look at from responsible AI. Now, if you take any major company, Google, Amazon's, Facebook's, everybody has the responsible AI principles, which are very similar, and they have their own frameworks by which you can have a path towards it. So, but more or less, you'll find the same theme underneath it. The first part is reproducibility. You want to standardize your machine learning pipelines. You want to have concerns like data model, data catalog, model catalog. Transparency is very important, and that's the main theme for this talk. You want to have interpretability and explainability of your machine learning models. This becomes very important, like persistent place in banking and healthcare. I mean, for us, we need to justify what models we are building to the customers and why certain decisions are being made. Fairness against unwanted bias is very important, just like the Apple Card case study, which directly gets into accountability. So the big question often that comes into ML discussions is when you bring human in the loop, how much automation, how much trust do you put in the ML system to start making decisions? I mean, you know the famous case of the self-driving car, which is still a debate. Like there were some accidents that happened, and then the big question was, can you trust the self-driving car? What are the ethical principles behind it? So accountability becomes very important. So even and I'm not talking at an AGI level, like artificial or general intelligence. So even at a very narrow AI, if you're building a model to make a loan prediction, you want to consider the accountability of it. You want to consider at what point, which data points you want to bring the human in the loop, and you want to consider what metrics of fairness, bias are associated with the model. And then the last 2 areas which are very important are security and privacy. Security gets into more like how do you protect your machine learning model. So there are technologies like encrypted computing and adversarial testing. So you want to be, many times there are especially in research, you will see adversarial attack against models. For example, there was a computer vision model which was detecting stop signs. And then you can just put a sticker on the stop sign, a small sticker which is not even distinguishable for the human eye. but the system gets fooled. It doesn't detect the stop sign. There are some glasses that come that are designed by scientists, which can actually feel a full facial recognition system. So whenever the facial recognition system, which you must have seen these systems in security cameras, which mark a square on your face, once you wear these glasses, the system gets fooled. So there are a lot of adversarial attacks that can happen in a machine learning model, and we need to be aware of that. And the final pillar, which is gaining much importance, especially now with a lot of the Facebook news that you hear, privacy of data. I mean, the big companies who are collecting our data, there needs to be accountability on what the data is being used for. Especially there are regulations like GDPR in Europe, and there is a California regulation also, which mandates that there is minimalistic use of the data. Unless you absolutely need it, do not collect any sensitive data. And even if sensitive data is collected, you want to generalize it. You cannot have individual records stored in a database. So there are technologies like federated learning and differential privacy, which tend to help in keeping the data more private. In short, federated learning basically what it does is it is a pattern to create machine learning models. Your data remains on the nodes. All you do is share your model updates. So keeping the data on the nodes, you just share the model updates. So no physical data gets transferred to a different machine, and that's the level of privacy you get. Differential privacy takes a statistical route. It adds noise to your data so that there is a plausible deniability where you can you cannot be sure that a particular record was there in a database or no. So it tries to compare the presence and absence of a record of an individual in a database and tries to measure that distance. So it gives a mathematical guarantee of privacy or mathematical definition of privacy. And differential privacy gets into, it's a very interesting topic for those interested. You can define things like a privacy budget. So you want a smaller privacy budget, your constraints are very tight so that your data, you add more noise to it so that your data becomes very sensitive to privacy, but then you may mess up on the accuracy side. While if you increase the privacy budget, the accuracy may be better. So there are a lot of concerns, concerns and a lot of libraries around it. But let's get back to the topic. Let's focus on transparency. So the first part of before getting into transparency would be standardization that we talked about. So we saw in that nice paper diagram, the diagram from the paper that we had, where the actual ML code development tends to be very small, but there are a lot of effort that is spent in management of the data, model development, production deployment, and model lifecycle. So in each of this area is a very dedicated topic like data management. There is a data ops discipline that is coming up where you can actually build pipeline and the focus becomes data as a product, where data becomes the product and you're building things around data rather than focusing on the applications. Versioning of data becomes very important. I mean, I'm sure some of you remember traditionally you would just go to Kaggle or something and pull a CSV file and build a machine learning model. But in an ideal setting with responsible AI, you would want to have a data catalog. It could either be the data maybe in S3 or in your database, but some way to manage the lineage of your data. So when you say version number 1, that is the data set that comes, and all the data scientists work on that particular data catalog. Similarly, from the model deployment side, we talk about low code. Low code is becoming very popular, especially things like AutoML, automated machine learning, which can help you with feature engineering as well as which can help you identify algorithms. In fact, in my demo, I'll show a very quick example of AutoML where we'll search through different models and find the best model of interest. And then production deployment, like we said, model serving, A/B testing, model lifecycle, having a model registry. So there are a lot of open source tools which can help you realize these patterns. So the way I see this, each of these is a pattern. Data catalog is a pattern. Model registry is a pattern. So when you are building machine learning systems, you don't want to replicate this pattern again. You would want to use a tool like PyCaret or DVC or MLflow, which already has the best practices built in. Now, you may also go to a hyperscaler, like if you look at Azure Data Studio, Databricks, or Amazon SageMaker, a lot of these machine learning platforms already have these patterns built in. So the key thing is to understand these patterns, understand which patterns are applicable to you and how do you implement them. And the actual implementation may be in an open source tool. You may customize something if none of these tools work for you, or you could just use one of the popular platforms. So let me take an example, just a very quick example of how this would mean for an ML system. So traditionally, I'm sure hopefully most of you will be familiar. If you look at a machine learning development, you will have a data preparation, model development, testing cycle. And this is typically done by the data scientists in an ML development. And this development environment could be just a laptop or could be a cluster on AWS or a GPU cluster. So this is a development environment where the model training happens, testing validation happens. Once the data scientist is happy with the statistical metrics, so you check for things like this confusion matrix, your true positive rate, false positive rate. You check for the receiver operating characteristic curve. So under the ROC curve, what is the area that will tell you the predictive power of your classifier or your model. And then once you are happy, you can deploy the model. So today, the most popular method is to deploy the model as a microservice. You package it as a container using one of the libraries, one of the frameworks that is available. And then you handle the logging of the data. Now, logging can be typically if you're looking at something like Kubernetes or as a deployment environment, you would be logging for service parameters. So you would be logging how many requests came in, how many requests were handled. Some of the requests were failed, and you would want to see that. What is the availability of the service? How often was the service up? So these are like service level performance metrics. So this is typically the development environment metrics and monitoring is what traditional ML cycle is. Now let's add the first pillar to it, reproducibility. So I would make it reproducible by looking at patterns like data catalog. So while you're doing data preparation, let's not have a CSV file, like a file structure with CSV files or custom database queries. Let's use a tool like DVC, data version control, which can manage your data versions. And there are multiple tools. I mean, most of this talk that I'll share, it is tool agnostic. I'm just showing some examples, but the important thing is to understand the pattern. So something like a data catalog, which will tell you what is the version of the data, so that when you're pulling the data, when you're telling a fellow data scientist, hey, I get this results, they know exactly which version of the data you're pulling so that they can reproduce the results. When the model is ready, instead of directly deploying to production or putting it in a developer's folder, let's push it to a model registry. And the model registry can be the one where all developers, the production ML engineers can pull the model out. This is like your traditional software development artifacts. Your machine learning model is also an artifact with model registry as a artifact store. And then more mature organizations look at feature store, where not just the data, but you actually do some feature engineering and create the features and make the features available as a feature store. So both for model development and for inference, you are using the feature store. So you have the same common data pre-processing done on the model. So this is one way to introduce reproducibility. Let's look at transparency. So if you want to make this more transparent, now along with your statistical performance, we would want to look at feature importance. So when a model is built, and I'm assuming a classification model, but there are ways to do this for all other types of models also. So once a model is built, you would want to know which sort of which features the model gives priority to. So if I make a prediction of a loan as reject, why was that rejection done? The number one factor was credit history. So this explanation is very important, and when this should be made part of the testing. So when the model is tested along with the unit tests, you want to test for the explanations of diverse data set, of diverse cases, to make sure your model is actually having the right tenets of fairness. Same way when you actually deploy in production, you want to monitor for data and concept drift. So no model is perfect all the time. I mean, once you deploy the model, very soon the data, the patterns of the data will change. So there will be a drift in the data. And this was very prominent with the recent COVID situation, where there were supply chain models that were predicting demand for consumer goods. But as soon as COVID came, the people started working from home, their lifestyle changed. So the demand patterns totally changed. And some of these models actually failed. So you want to be able to know the data drift that is happening and check if your model can handle the data drift. And if it cannot, you want to have a message saying that, hey, this model is failing. And that is what the concept drift will tell you, that the relationship between the dependent and independent variables is changing. and then you would want to resample the data from the new distribution and retrain the model. And the final part of it is accountability, probably the most important part. Now, all this is happening, but you want to control where the human comes into the loop, especially for fairness bias. This is very important. I mean, you can say that my model is biased on a particular feature, but the decision that that feature is a protected attribute and being biased is not the right thing has to be done by the human expert. So you have to have the right tools in place wherein the human can be brought in the loop, and this bias and model performance can be evaluated. And then one other aspect which we'll show in the demo, I won't get too much into it, is the causal studies. So I'll get to it in a little detail. So these are the three things, three pillars of responsible AI: reproducibility, transparency, accountability, that you want to consider when you're putting models into production. Now, since we are focusing more on the interpretability of it, or the explainable AI, explainability of models can be looked at 3 stages. So let's talk a little bit about that, and then we'll get to the demo. So the first stage is the choice of the model. So when at Persistent, we look at banking and healthcare, which is more very regulated spaces. So we need to be accountable when the model is, when we build a model, we need to be able to predict or we need to provide what are the inner workings of the model. So the model should be able to explain itself. Now, this is a nice slide from DARPA. It's from a public domain presentation that they did, where they, I mean, this is more of a thought experiment. They compared the learning performance with the explainability. So we see that as the models get more complicated, like you start with something like linear regression or a decision tree, these are very inherently explainable. Like if you look at linear regression, you know the coefficients of the hypothesis that you're making. So those coefficients will clearly tell you which features are important. But then as you get into more details, where you get into things like this Bayesian networks and ensemble models, then your explainability becomes less. So these models get less, like if you move up the curve, your performance increases when you go into deep learning, but your explainability becomes less. So this is something that is more a generic term, and you need to be aware of that. So the first decision you would want to make is, do you want a model which is inherently explainable, something like random forest, linear regression, but knowing very well that it may not be inherently, the performance may not be to the mark. And then if you're making a decision to go to deep learning, you should know that you should have to work to get an explainable explanation out of it. Now, there are other special type of models. If you look at, and this is one of the recent models from Microsoft called explainable boosting machines, EBM. If you get a chance, do read through the paper on EBM. So this kind of combines the best of both worlds. What it does is it takes something like linear regression, but in linear regression, you are actually considering that the y is just a linear sum of the weights. So linear combination of the weights of the x's. Sorry. So any weight multiplied by x, you just add them, and you get the value of y. Now, what explainable boosting does, it uses a technique called generalized additive models. So each of these terms, instead of a simple direct relation, a linear relation, it makes it more complex. It makes it non-linear. So it could be a small tree for that particular feature, and these trees get aggregated together so that you add non-linearity to it. So these models become more explainable. So you know exactly how much importance each of these features has. So these are modern models. In fact, if you look at one of the domains that is becoming very popular in the banking world, which is model risk management. Model risk management talks about, and Wells Fargo, one of our customers, is very big in this. They look at what is the implication of a bad decision made by a model. And so they want to know the actual predictions for a model, and these models to be inherently explainable. So a lot of research papers published by Wells Fargo are around this topic of how to build interpretable machine learning models. And this is definitely a much more area of focus. And just for those, and I know most of you must be familiar with things like SHAP and LIME. Now, SHAP and LIME try to build proxy models for your, so whatever the model is, they will try to build a proxy model and try to explain it. So they are not actually telling you what the model is. They're just playing with the model with different data set and trying to make a prediction. So it is still a black box approach, but using the data and using some perturbations in the data, they're trying to make a prediction. While these models, which are more glass box, they call it, they try to take the parameters from the model and based on that generate the feature importance. So that is one aspect of it, comparing black box versus glass box. The second very important part is causal analysis. And this is more relevant in the medical domain. So I would suggest, I mean, if it is something that in your domain is important, you would get into it, but you should definitely be aware of this. So this is a classic example of this. And we hear the term correlation does not mean causation. So what most machine learning models tell you is how the features are correlated, how the x's are correlated to give you y. But that doesn't mean that this x will cause that y. So this is a classic case where we looked at the data, and this is one from the internet. In the references, there's a source. They looked at the cases for pneumonia and which cases had asthma and which cases did not have asthma before. And they saw that the risk of death for the cases with asthma, it was lower. So if you look at this, when the has asthma is no, the risk of death is higher, risk of death by pneumonia. So this was a very interesting observation. So if you would build a machine learning model only with this much information, you would think that having asthma is a good thing. That because if you have asthma, your risk of death is low. But this is actually just a correlation. It is not a it doesn't mean that asthma is helping you reduce your risk of death. What this study missed, I mean, when they did the study, what this missed was there was another factor, which was ICU admissions. So the people with asthma, when they come for treatment, and if they are having a shortness of breath, they would be immediately put into ICU and they would be stabilized. So because they are directly related to ICU admissions, they would the risk of death would become less. While people without asthma, they would the studies showed that there was no urgency to move them to ICU. So that kind of impacted the risk. So there was one more factor, the admission to ICU, which was the deciding the factor. So because admission to ICU decided on the risk of the death, and that was affected by having asthma or no, that is why having asthma or no was affecting risk. So this is in causal analysis is called confounding variable, which is affecting both x's and the y, and it is actually making the decision, but you feel that this x variable is making the decision. So this is the classic case of causal analysis. So causal analysis, counterfactuals, I mean, this become very important as you get into the medical domain. And in the demo, I'll try to show an example of how to do this analysis. I mean, these terms typically tend to, I know even when I started with this, it was very overwhelming to do this causal analysis. But today, actually, there are libraries which can do this analysis very easily for you. Only thing, they need a lot of data to be effective, because unless you have lot of data, you don't know. You cannot do this analysis, but don't get overwhelmed by the terms. I think it's important to understand what they mean and how you can use this. So this causal analysis is another thing that you should consider when you select an algorithm, because just if I give you some explanations and these are correlation based explanations, you would want a domain expert to verify that are we doing the right thing, or are we having a complete picture? Are we missing the data from the ICU admission? So you want to make sure the first level, when you're considering explainability, you want to make sure that you are considered all the factors, including possible confounding, and use that for your analysis. So this was the first stage. I'll go a little quick because I do want to get to the demo. The second one is more around business justification. So once you build the model, you have a model and you can make either global or local explanations. Global means you are finding explanations on the entire model, on the whole training data set. So this was a case that this was an experiment we did actually. We had two data sets, version 1, version 2. Dataset version 1 actually gave us a lower area under the curve, 0.76, while the second dataset was higher area under the curve. So this was obviously performing, you see the bigger area, and it was performing better. But when we build the model and we actually check the explanations, we could see that the first dataset was more fair. It was looking at credit history, loan amount, application income, while the second dataset started looking at things like gender. So gender was playing a role in this data set. And these are doctored data sets, so this hopefully not the real world will reflect it. But in this example, gender was playing a role. So there was some bias on gender in this example. So we could not consider dataset version 2, or we had to do some doctoring to reduce the effect of that particular variable. Similarly, this is another example. This is more around customer churn detection, where uh, we could look at the total charges and the tenure. And this is a public data set on customers from a cable company. So we are just plotting two variables, total charges and customer churn. And the orange means customers who have left. Churn is customers who have left the company. And blue is ones that have not left, and they're still loyal customers. And we could look at, so this is almost like a 4-dimensional plot. You're looking at X and Y, and you're also looking at one particular factor, which is the contract, which is month to month, 1 year, 2 year. And then the fourth dimension is the color telling you which customers have left. So we clearly see here, just purely from data analysis, there's no ML here. From the data analysis, you can see that for the month-to-month contract, there is more churn happening. So this now this is the example of a bias that you want to find out. The data set is biased on month-to-month, but that is reflecting reality, that because the people have month-to-month contract, that is affecting your churn. And this is something you could even find out just by looking at the data set without any ML. And truly so, when we actually build a machine learning model, we actually went ahead and built an explainable boosting machine model for this using Microsoft's library. And contract was the #1 factor. So because of the contract, this was the churn was high for those customers. So this sort of analysis is important to understand the business validation. This is again where the accountability comes into play. This is what your data is saying. You want to bring the human in the loop, a domain expert, to say, does this reflect reality? Are you seeing that in the real world, that because the contract, your customers are tend to leave who have a month-to-month contract? And this verification needs to be done. So that is the second stage of explainability. And the final stage is one when you actually make predictions into in production. So you're deploying the model to production and you're making predictions. And here I actually I didn't want to show just tabular examples, because explainability is valid also for text data, unstructured text data, or images. So this is an example of text data where we used actually a transformer model, and it was doing sentiment analysis. But using the SHAP scores, we could say that this is why so in this example, it was saying this sentence was categorized as sadness. And the reason was these words that are highlighted in pink were more, actually it's the other way around, sorry. So there was, there were the other words which are highlighted in blue, like humiliated, dissatisfied, pathetic. So these words kind of focus more on making a decision on why that particular categorization was done. So you can look at an individual prediction and generate an explanation, either a text explanation or a tabular explanation, to generate why that particular decision was made. And then final analysis, and this will get, once we get into the demo, I think this will be much more clearer. This is more around error analysis. Like when you present a model for inference saying that accuracy is 99%, you also need to know how well the model is performing on all cohorts. So error analysis is a very important tool for doing this. So with that, I don't want to take more time. Let's keep 20 minutes at least for the demo. So so while I switch to the demo, and any intermediate questions, or we can take it at the end.
We can take, we have two, three questions. Can we take that if the answers would be within a minute, so that the demonstration doesn't get late?
Yeah, sure.
Okay. So the first question was, how would it affect the output if that particular feature, that is gender, race, etc., are not included as an input variable? Yeah,
that's a very good question. So, and that is actually, there was a very nice paper on fairness through unawareness from IBM AI Fairness 360. The short answer is it will still affect, because these features tend to be correlated. So even if you remove gender, there will be some effect of gender on other factors, which will be hidden. So ultimately, when you and you can do that experiment, actually, you can take a data set, remove gender, build a machine learning model, put the gender back, and see the predictions, how the gender affects the predictions. We actually did that, and you could clearly see there was a bias on gender. So so you should be very careful on that route. and I know in real world it is difficult to get gender. You have to play with whatever data is given to you. You may not have the privilege to go back and get it, but if you do, you would want to at least experiment that, put the gender back in and see how the results vary, at least the ground truth, how it varies, because you would at least know that there is a bias and you would want to figure out how to handle it. That's a very good question.
Again, there's a question after this from the same person. Is it because of PCA?
Well, PCA, well, yeah, it's kind of, it's because of the variance, I would say. PCA, I mean, if I understand you right, is more, it is just going to get you all the variance. Uh, Basically, it will take your features and it will give you a reduced number of features, which captures the variance. So yes, I would say the gender will play a role in making this variance. So when you do a PCA also, you will get the same results, if I understand you right.
Okay. We'll take one more question, Dattaraj, and then we'll go back to the demonstration, and the rest of the questions we'll take it after the session. How do you handle the missing values?
Yeah, so I'll show an example of this in the demo. And you kind of, and this is a much more topic. So you typically, some quick tips I would say is, one is you would want to look at a percentage evaluation. And there are ways to do this in Pandas where you can see how much for each column, each feature, how much percentage of values are missing. And you typically set a threshold that above 30%, if they're missing, you would want to omit the feature. The other option is if the values are like say 10-20% are missing, you would want to do some imputation. And I'll show the imputation example. You can do mean imputation, mode imputation for categorical, or you could do average imputation, where you just fill in the missing values with average. Obviously, you're generating new data here and it may not reflect reality. But and that is again where you want to contact the domain expert, that is it okay if I have some missing values, say for co-applicant income, can I just put a 0 there, or I put the average for all the values? So this is again something you have to go back to the domain expert and make a decision. But from the tools side, I'll show you in like 5 minutes an example of this, of data imputation, which could be used there.
Okay, Dattaraj, we can continue with the demonstration. Other questions, we'll take it at the end of the session.
Okay, great. So let's so this demonstration, and you can see I'm just going to show this in the Jupyter notebook. So it's purely code. There won't be any UI screens or something. So and again, one more, just coming back to what I said. Don't worry about the tools. I mean, these tools keep evolving. Tomorrow there'll be better tools to do this. Try to understand the concept. There are two concepts I'm going to show here. One is the low-code model development. So I'll use PyCaret, which is very popular library, to quickly do feature engineering and build a machine learning model. And second is the responsible AI dashboard. This is from Microsoft. This is a very good tool. I highly recommend you to look at it. It's an open source tool. It combines a bunch of tools like EconML. It combines these different things like error analysis, interpretability, fairness, and puts in a single pane of glass. So you can quickly. So in this, what I'll show is I'll take a model built in PyCaret, take the features that are generated, put them to the Microsoft responsible AI dashboard, and show you the dashboard, so that you don't need to do any custom feature engineering, and all the imputation the gentleman asked before, that can also be taken care of. And in a single pane of glass, you'll get to see the ethical aspect. I mean, you'll always see the MLOps pieces like accuracy and all in PyCaret, but you'll get to see the other aspects, causation and all, in this responsible AI dashboard. And I can make this available also for those interested. So let me just quickly load the data. So this data set is basically a loan approval data set. This is from one of the Kaggle competitions, I think by Analytics Vidya. So what it does is it has the gender, married, dependence, these different your standard credit history, property area, etc. Loan status is the target, which is yes or no. Yes is loan approved, no is not approved. So first, without doing any machine learning, let me look at some of the features. So I'll say, hey, married and gender look like protected. They probably should not be affecting the loan approval. So let's see if there is a bias. So this is a simple chart, and this code is there. I'm just doing a simple bar chart on looking at the loan approval status versus gender and the count. So you are seeing both in So for the gender and for merit, we are seeing there is an almost equal distribution. So there are the negatives and the positives are almost this in a similar proportion. So there are less negatives and more positives in both cases. So which is fine. Just for an experiment, I'm going to load one more data set, which is a doctored data set, which has some bias. And if you look at that data set, the same experiment with that, you will see that now for the loan status, uh, for a male participant, there is a lower proportion of no's compared to yes. While in case of the female participant, female applicant, the proportion of yes is proportion of no's is high compared to yes. So just purely from charting from pandas, you can see that these two data sets differ, and there is a bias on gender in this data set. So this is a quick and dirty way of first analyzing, and there are multiple packages. You look at H2O, Data Robot, they can do this directly for you, give you this sort of charts. So just looking at two versions of the data set, you can see that there's a bias in one data set compared to the other. The key thing here is you need to, I've just used CSV files here, but you would want to have a data catalog where your right version of the file is coming, so you know which version of the data set is biased. And then this step should be the same, that all data scientists could use this as a template to say that, okay, let's check for bias. And then there are tools like IBM AI Fairness 360. Right now, I had to plot this and show the bias. There are metrics like statistical parity difference or disparate impact, which can give you which can just look at the data set, look at the predicted attributes, and tell you that the disparate impact is high here. That means there is a presence of bias. So just through metrics, you can also measure this presence of bias. Now let's go to the low code part. So PyCaret is one of my favorite libraries. So all you have to do is set up the experiment, and PyCaret gives you. There's not much fancy PyCaret does. It writes a lot of boilerplate code for you. So there was a question about imputation. So you can specify which features to ignore. You can specify for categorical imputation, I want to say mode. So whichever is the most common. So whenever there are missing values in a categorical column, whichever is the most common value, I want to use that. Now that's an assumption I'm making. Of course, I will have to verify that with a data scientist. The other option is I can drop all columns, like drop NA, but then you're losing valuable data just for one column. For a numeric value, you can do a simple imputation where you can just, I think it's just filling up with means. So now it just, this is a very small data set. So it directly did all the feature engineering, because basically what it did was it removed all this labels like graduate and all, and did a one-hot encoding for that. So a lot of that boilerplate code, PyCaret did it directly. And I can see the results of this. So I can get a configuration. So you could see from the previous one, it didn't touch the numerical features, but all the categorical features were one-hot encoded. Then I'll run a training on it. So this is another more like an AutoML feature that I can do a compare models. So what it is doing right now, it is taking my data set and the feature engineer data set and comparing multiple models. It's comparing basically shallow models, random forest, rich classifier, naive Bayes, etc. And what I have told is I want recall as a parameter. So as you know, there are multiple metrics like accuracy, recall, precision, F1 score. And depending on the scenario, different metrics are more important. So in this case, I'm saying recall is more important to me. So from recall, it created a leaderboard and told me that random forest classifier on this data set is the most appropriate, which is giving me a 90% recall. Now, keep in mind, it's not doing deep learning. So there are other packages like Data Robot, which will do the same thing for deep learning, which is much more impactful. But let's continue with this. So I'm selecting this model. I'm just going to plot this. This is the receiver operator's characteristic. Let me predict the model. And when I predict the model, you will see that it created a test data set with 96 rows. And for that test data set, I'm getting the 86.6% recall and AUC of 80%. So this is the final outcome. So typically as data scientists, this is where we tend to stop. That, okay, we took the data set, we did feature engineering, we built a machine learning model, we showed the results. Now, these 96 rows that came out of my test data set, I have a blanket number like 86% recall on this. Now, can I dig deep into it? Can I get into it and explain that further? What does that mean? That for these 96. Because keep in mind, here we are working on open data set, but in the real world, there are annotators who have spent time annotating this data, even the test data. They have spent time labeling the data. It is very valuable. It is difficult to get quality label data, and this is quality label data. So we want to make the most of it. So especially in regulatory domains, we need to, when we give an explanation, we need to make sure we explain these 96, how is the distribution of my prediction? And that is what Responsible AI dashboard does. Again, it's a combination of multiple tools. There are IBM also and Google also has tools to do this. You can use any of them, but let's look at the concept. So these are the columns that I have, and these are the size of my test data set. So I'm just looking at the categorical columns, and this is these are just the 10 lines of code. So building this dashboard is just this 10 lines of code after you're done the feature engineering, and that is something that I really like, that in PyCaret it does all the one-hot encoding and takes care of the feature engineering and gives me a dashboard with these 10 lines of code. So what it is doing when I run this 10 lines of code is it is analyzing, and this will take some time. I'll show you the dashboard which is already created, but it is analyzing each record out of 96 and getting into details. It is getting to things like explanations for it. It is getting to things like counterfactuals for it. And let's see the results for it. So while I let it run, I have the dashboard run open here. I'll pull that up. If I can move this here. Okay, so this is the one of the view. This is the view of the dashboard, and it has multiple panes of glass. So it is actually creating a dashboard in a separate. It is hosting it on this machine. So now at the top, the first analysis is error analysis. So what it does is it tells me that the error rate is 26.04%. So like I said, it was 84% accurate. So or 74% accurate. So 26% is the error rate. And this is for the entire data set. For all 96 data points on my test or validation data set, this is the error rate. So what does it mean? Which cohorts or which groups have a bigger error? So I can do that with this error analysis. So I can click here, and it, from its own analysis, found out that any applicant who is greater than 4,000 units of income has a bigger error rate. The error rate becomes 38%. Within that cohort, I can select one more cohort, which has an error rate of 44%. So you clearly get to see that, and especially in the regulated industry, when you present that, hey, my metric is 75% accurate, but on this cohort where the property area is not semi-urban and the income is very high, my model doesn't do a very good job. It gives me like a 55% accuracy. So this is the error analysis you can do, and this tool is kind of it's from Microsoft. It's an open source tool, and there are, like I said, there are other tools also from Google which can do the similar thing. But the concept is, once you have instead of blindly going with an accuracy number, you would want to drill deep into your testing and validation data set and understand where your model is failing, which cohorts or which groups the model has less accuracy, and want to highlight that. And that is the one aspect of transparency. Next, this is just a model overview. It will tell you, compared to this cohort that I highlighted, what is the accuracy levels. Now, this is interesting. When you go to the data explorer, now this is what we did earlier with that code. Now I can select the true Y, and instead of lone amount, let me select the gender male, and you could see a similar plot. So plots like this can easily be done either through code or through tools like this. But the interpretation would be, now this data set was a good data set that I used, unbiased data set. So if you had a biased data set, you would see the difference in the approval rate or selection rate, and you would be able to highlight that. Next is feature importance. This is again very important. It is doing I think it uses SHAP, and it does a global feature importance. And you can clearly say that, see that credit history is #1 here for feature importances. Now, feature importance is one of the main parts of explainable AI, but then it is also, it can be at a global level or a local level. So global level is the entire model on the entire training data set or validation data set. These 96 points. At the global level, it is, the credit risk is becoming the #1 factor. But I can do it at an individual level also. So I can select one particular point. So and it divides the correct and wrong predictions. So I can just say, for this, for one of these predictions, this is the so for this particular case that I selected, I'm seeing that the explanation for this point is not credit history, but loan amount. So in this particular case, because of loan amount, that decision was made. So it is possible that a point inside your validation data set may have a different explanation. So it is important to look at the individual explanations also, which will tell you, and especially like I said, people have spent a lot of time labeling those 96 data points. You want to give them enough credit and understand how some of these points are varying. And then, so this is more around explainability. And again, these are more using things like shape and line, which are not glass box models, they are black box models, but they do a pretty good job of explaining your individual predictions. Now, the next part of it is, now let me actually take a prediction where it was denied. So row number 62 is where the value was denied. And looks like that it was denied because of credit history. That is the reason why the loan was denied. So counterfactuals is a very interesting case. Now this gets into the ladder of causation, where you're looking at counterfactual explanation. So this is another aspect of explainable AI. Counterfactual tells you what different you should do to change that particular prediction. So here the prediction is loan denied. What can you do differently to make that prediction approved? So let me take that point 62, which we saw earlier. Yeah, and I'll create a counterfactual explanation. Again, this interface is pretty good from Microsoft. And what it is telling me is that to change the label from 0 to 1, these are the factors it will affect. You would want to change the credit history, obviously, if you have a better credit history. And we saw that from the explanations also, that credit history was the #1 factor. So changing your credit history, improving your credit history would be the #1 thing to influence your decision. Co-applicant income and applicant income, if you can increase it to some level, it can improve. So it directly gives you a bunch of counterfactuals, and some of them may not make sense. Like if they tell you gender or something, that wouldn't be something feasible. So you have to kind of, again, bring the human in the loop, understand which factors are important. And this is a very small toy data set, so you don't really get much here. But if you had a really big data set and many features, you could actually get some actionable items from here, saying that your loan approval will be better by changing these features. And that could be something very important. So you're actually now getting into the action piece of it. Now, so far we were into correlation, where we were finding which features were important. Now we are getting into intervention, where you actually we can say that, hey, by changing this, we can change the decision for the loan prediction. And the final aspect is causation. So this is something, this is a whole deep topic, and there are books written on causal analysis, so I won't go into details. But what it does is, there are two factors which, I think I didn't mention that. In the code, there were two factors that I asked it to consider: credit history and self-employed. Yes. So I wanted to do a causal analysis on these two factors. So it did that analysis, and it tells me that credit history is very much impactful. That the impact is 0.75. That means by changing one value of credit history from 0 to 1, I can change my approval from 0 to 0.75, which is 1. So credit history is the #1 factor, which is going to affect my. It's a causal relationship. Credit history can cause you to lose the loan, and it is doing a lot of analysis, data crunching, and this is a very small data set, so it may not be that effective. But you have a bigger data set, you can actually get some really interesting causal analysis, and you work with your domain experts to see if this causal relationship makes sense. And then self-employed actually had a lower relationship on credit history, so that was not in this particular data set. So if you have more data in a different case, you can get more. But the point is, it can do this causal studies and say how much impact each feature has on a particular data set. So in a summary, this demo kind of showed you starting with your data set, doing a low code analysis, showing your accuracy metrics, showing your ROC curve, and selecting a model using AutoML. And then for that model, along with your accuracy numbers, doing a responsible AI analysis, looking at explainability, interpretability, looking at what if analysis, causal, counterfactual, and causal studies. So you can do a lot of analysis on the data. So I think this is, even if you don't have to do this in your projects, it's important to know this, because as you get into more domains, when people start questioning models, you need to have this data handy that this is why your model is behaving in a particular manner. So I highly encourage you to look at these tools. These are open source tools, very much available. There are a bunch of articles in my in the slides that I'll make available, which actually talk about some of these. We also have at Persistent have some videos around this on explainability and MLOps. You can have a look at some of these. So yeah, so that I think I'll end here. Those were some of the things that I wanted. I hope the demo was clear. I mean, the screen was refreshing fine, and we can take questions. Which are the you could see the demo, right, properly?
Yes, I could see it. It was crisp and clear.
Excellent.
Okay.
So yeah, let's take some questions.
Okay. How can we leverage responsible AI with MLOps?
Yeah. So I think I hope I mean, this demo was the whole point of that. So hopefully it will answer that. I guess the question was before the demo, but
yes, it was the very first question that we had.
So I mean, this is just one way of doing that. The thing is, as a data scientist, you need to know what are the facets of responsible AI, what libraries are available, what techniques are available, more importantly, to do like this error analysis, the interpretability study, to do your analysis. And then when you do your MLOps, now MLOps, typically you use a tool like MLflow, you record your metrics. So along with recording your precision recall, you want to recall, you would also want to record fairness metrics, so like statistical parity. So whenever there's a new data set, you may not have time to actually analyze the data set fully. But if it is part of your MLOps cycle, checking for statistical parity, you can quickly, whenever the CI/CD process happens, statistical parity is one of the metrics that comes out. And you can quickly have a look and say that, hey, looks like there is some bias in the data. Then more complicated things like this error analysis would be needed when there is, especially when there is a regulated environment. I hope I answered the question.
Okay, thanks, Dattaraj. Next one is, which tools will help us to remove the noise from the data set?
Yeah, that's a good question. So removal of noise. We saw some of these things like the imputation tools. So especially for null values, you can get rid of those values. There's a lot of manual feature engineering you can do. If you know that a value should be between certain range, you can write code to get rid of outliers, or there are some libraries which can record outliers for you. Some other tools are there, like there's this technique called SMOTs. I think it's the minority oversampling technique. So they can also, because a lot of times there is a imbalance. You get, I mean, your sampling becomes biased, so that you are only going to collect samples which are easy to get. But the real world may not be that. There are complex samples also, and you don't have enough data. So that will be noise, that there is too much too much data from one category and not enough from this. So in that case, there may be some simulations you could use, like this SMOT method, minority oversampling technique, to do this. So yeah, there are a bunch of feature engineering tools, but I don't think there is like, I mean, these libraries like Data Robot, H2O do provide bunch of tools.
Okay, thank you. The next one is, since testing is so important in the pipeline, any reason why the huge error of bias in gender was not detected in case of Apple Card?
Yeah, that's a very good point. And obviously that the details are not revealed because there is a legal implications on it. So my 2 cents would be that I don't know if the testing was done, like somebody asked the question, just let's remove the gender out of it. So you don't even consider gender. So if that gender is not a feature, then you wouldn't even think that your data set will be biased. That's the typical fairness through unawareness. So even when you get to a testing, you would start with the basic data set. So in the basic data set that you have, if it doesn't have gender, you would not consider gender as a valid feature. So it goes to that level where you would want to actually even think like, and that is where the human in the loop and domain expert is important. You want to get to the level where don't worry about what data is available to you. Don't have a sampling bias. Think of what data you would want to look at. So consider bias as something not as a taboo thing, or that feature as a, or sorry, don't consider the protected attribute like gender or race as a taboo thing, and don't keep it out. Take it in, but consider it and understand if there is a bias. So I think, and this is just a guess, I cannot comment on Apple's strategy, but I think one of the things that what came out in the papers was that it was fairness to unawareness, that gender was not considered, which was a mistake. You should consider and understand the effects of it.
Right. The next one. Can imputation may lead towards biasness as all missing values are produced using the same method, that is average, mean, etc.
Yeah, that's a very good point. Actually, yeah, that it is true. In imputation, so you have to be careful with the imputation methods, especially, and that is why the first thing I typically do is check for the percentage of missing values. So if it is more than 30%, I'm personally I'm not that keen on using imputation, because obviously it is going to add bias. In fact, there are many cases where you just fill in with mean, and it will create bias, and it will actually give you wrong results. So yeah, you have to be very careful of the bias and the error that happens because of imputation. Very good point.
Right, thank you. The next one is, if gender has impact, why do we call it as a bias, as ML model was able to best fit the data that way?
Yeah, that is a very good point, and that's a good discussion topic. So the thing is, and when I say bias, often people say bias is bad, but bias is something that the model has. There is a learning bias. Even if even if the model says based on my applicant income, I'm deciding to give credit or no. That is also a bias. It is biased from applicant, but which is a learning bias, which is important for the model to make a prediction. So gender becomes some things like gender, race become important because there are legal implications, especially in US. If you look at the laws like fair credit law or equal housing law, there are clearly defined these protected attributes like gender, race, I believe even religion. These are the attributes where, and this has nothing to do with ML. These are laws defined, and I'm sure in India also there are equivalent laws which say that uh, the the credit application should not be evaluated for these factors. So just for a race, a person should not be given a low credit or refused a credit. So that is why this legal terms makes this. So it's a whole fairness study. This legal terms makes it into protected features. So that is why things like gender become. But otherwise, you're right. I mean, maybe the real world data says that historically people of particular gender have been rejected loans. So why not continue that? But that is what where the ethical AI ethics committee comes into place. That even though historically there is bias, because of legal, the law says that this bias should not be there. So you need to correct it. And as a data scientist, we need to be able to identify it and measure it. Good question.
Okay. Another question, there could be other reasons and inputs that may have given a loan is equal to N for female gender data. Don't we analyze that or consider it?
I missed that part. N for female.
N is equal to female.
Okay.
So it's like there could be other reasons and inputs that may have given a loan that is equal to N, N as in the alphabet N for female gender data. Don't we analyze that or consider it?
Yeah. So if I understand you right, it's more like just other than gender, what are the other? I mean, you would consider other features for the loan, for giving the loan. So that is true. I mean, you would want to consider those features, but because of the legal reasons, you would want to know the impact that these protected attributes like gender have on your loan. This thing, at least you should know. You should know what the impact these protected features have. I hope I got the question, or maybe you can rephrase it.
We hope so. Otherwise, we'll get it in the chat. That's what I'm also anticipating. Okay, the next one is, could you please tell what are the possible algorithms or ideas being used for what if analysis?
Yeah, so what if analysis, so one was the one I showed, the counterfactual ones. So this tells you that, hey, if I move my, if I change my credit, if I increase my credit, if the credit history for this applicant was one, the loan probably would have been approved. And then similarly, if the co-applicant income was so much, then the loan would have been approved. So one is this what if counterfactual, and this is actually this Microsoft dashboard is just a dashboard of multiple tools. There is this tool called Dice ML from Microsoft, which is something that can give you counterfactual. So you can tweak it. It will tell you the exact counterfactuals for each predictions. So that is one. Google has a what if tool that can also do the counterfactual analysis. And I'm sure if you look at IBM, there must be some tool. And a lot of this effort is in research stage. So if you look at the GitHub repositories of these companies, they will have. But two major, at least I know, is that Microsoft's counterfactual Dice ML and the Google's what if analysis. I think these two are pretty popular and pretty intuitive.
All right. How much data is enough data? What is the minimum data needed?
Yeah, that's always the question. It's not I would say that there's no rule of thumb. It depends on your specific problem and how big the problem is. If it's a classification, how many classes you have, and how much extremes can be handled by your data. Like if you're looking at loan application, is your data covering all aspects of loan, all the gender? Like you look at the genders, race, the different features. At least the extremes are covered, and the different scenarios are covered. Just like testing, you would want to test for all extreme cases. So you want your data set to have all sorts of, and I'm talking from the responsible AI aspect, all extreme cases. And generally, you would think more data is better for a machine learning model because it can learn inferences from it. So a few hundred records is typically something that is definitely for tabular data is recommended. And this one is pretty less. I think it's 500 records. So you would want to get into more of that, like even few 100,000 records would be something that is good. And if you want to get into causal analysis, now you saw that this counterfactuals actually is not very effective. I mean, it's just telling you change the credit history. That is all it is telling. So it is not covering all the extremities. It is just saying credit history is number one. Everything is linked to credit history. So there is not enough diversity in this data set because it's just a toy data set. But you would want to have like 100,000 odd records where all the diverse cases are covered. And of course, depends on the features also. Now here the features are very small, I mean 20, 25 features, but in real world, you will get like 100, 200 features. So you want to have a data set which will cover all extremes of the features and enough to actually make a decision. And you can know that. I mean, when you do the training, if there is a smaller data set, you will tend to get overfitting on the data. So you will get an idea of it. But yeah, not a direct answer, but these are the factors you would consider.
All right. Edge compute, like low-cost distributed compute, how can we distribute the data set among us for distributed reduced data for local analytics leading to global analytics?
Yeah, so that gets more into the federated learning and privacy preserving AI aspect. So and that actually, if you look at federated learning, one of the main, there are two aspects of federated learning. One is privacy, that you cannot physically share the data. Like if you have 3 hospitals and you're building a model in a decentralized manner, you're kind of, so if you're building a model in a decentralized manner, you kind of want to keep the data separate, and you cannot pull the data together. The second aspect of it is privacy, where second aspect is performance, where you have model on the edge device, like Google does with the Google keyboard. Like you have if you know the Google's keyboard, that uses federated learning. So over time it learns your patterns, but it doesn't want to share your text data. So it is more around performance. You don't want to share this data, and you want to have edge compute to improve your computation. So you can use federated learning for improved performance also, and decentralized net frameworks like there is a PySIF framework for federated learning, which can do these kind of things.
Okay. Suppose we are working on big data and we have a lot of noise and data is biased, but we don't know about it. So how do we deal with that? Some of the libraries won't be able to deal with this, especially for feature analysis of 1-by-1 row.
Yes, but then so typically, yeah, you are right. When you look at big data, it's a I mean it's a lot of data, and it's a separate way of analyzing it. But these libraries not necessarily do it one by one analysis. So typically you can do like a grouping, because even if it is big data, there'll be so many protected features that you want to look for bias. And these protected features you would want to analyze. Like if you look at gender or race, there'll be so many categories. So you would want to run metrics on those categories. In fact, these metrics that we talk about, I mean, every tool gives different metrics like statistical parity difference and all, but it's not rocket science. I mean, it is very straightforward to capture. In fact, I have a LinkedIn post. I mean, maybe I can give a reference to it. There is a simple Excel sheet that we prepared for one of our customers where we just took some samples and showed how to calculate statistical parity difference and disparate impact. So these fairness metrics can be calculated on big data just through, you can even write a simple Hadoop query or a Spark query to calculate these on groups. In fact, I think, and I'm just maybe overthinking this, but a MapReduce pattern would be even good to distribute your data on different groups and combine the results. So it's, I don't think big data would matter. It's just the way you're going to calculate your metrics on different protected attributes. I think that is what you should consider.
Okay. I know we are running out of time, but we'll take one last question, please, Dattaraj, if you're okay.
Sure. Yeah, sure.
Is it necessary to have GPU to train TRF module in SPACY? Can we train it on CPU?
Oh, okay. That's a good question. So more on the NLP side. So I guess it depends on the data set that you have, because if you're training, and TRF, I'm thinking is transformers. So if you're training a transformer model, obviously transformers would need a bigger data set, because their whole thing is pre-training on a larger data set. So when you have a large data set to pre-train on, you would need a GPU. So a recommendation is definitely for transformers on SPACY. You would want to run it on a GPU. Now, if you have a pre-trained model, if you start from a pre-trained model and there is just an incremental data set that you want to tune to, I think SPACY has some ways, especially the new version of SPACY, the 3.0 plus version of SPACY. You can run that on a CPU, but then it will be very limited. You will have to have a very less data and very limited. But yeah, it is possible to train on a CPU. But my personal thing, I would say get a GPU on like Amazon SageMaker Studio or Google Colab. I think that's free and you can quickly train this thing. So I don't think many sources of GPU are available for free also. So I don't think that should stop you.
Thank you so much, Dattaraj, for the wonderful session. It was absolutely inciting. And thank you again, for patiently answering so many questions for the past 20 minutes. And audience, thanks a lot. You have been quite interactive with, the questions that were coming in. If your questions are not answered in the interest of time, you can mail us your questions at pune@nasscom.in, and our team will get in touch with you to get those answers from Dattaraj. Thank you so much, everyone. Thank you, Dattaraj. And everyone, please do help us with the feedback post this webinar. It will be very helpful for us. Thank you, and have a great evening, everyone.
Thank you. Bye.
Bye.